My name is Caner Tol. I'm a PhD student at Worcester Polytechnic Institute. And we have listened to defense papers, so hopefully this will be a motivation to those defenses. So I'll present our work, Jolt, recovering TLS signing keys via Rowhammer faults. As many of you know, digital signature schemes are cryptographic algorithms which are designed to ensure authenticity, integrity, and non-repudiation in digital communications and transactions. And they play a crucial role in many applications, and they also provide integrity during the handshake phase of security protocols such as TLS, SSH, and IPsec. And NIST standardized these algorithms in FIPS 186. And in this presentation, I'll focus on ECDSA specifically. So we have an attack on these signature schemes, but what is the threat model? So the attack we have is an active software on the fault injection attack, and we assume the victim is running in an environment which is logically isolated from the attackers, and it signs messages using the signature scheme such as ECDSA, and the attacker is somehow collocated with the victim. It can be through a shared class server or a browser which is running on the victim's machine. And from time to time, it injects faults into the victim's memory space using Rowhammer, and specifically it's targeting the private signing key. And resulting from that, the attacker collects the faulty signatures, and finally, using these faulty signatures, it recovers the private signing key. So in this work, we propose a signature correction attack called Jolt, and it has three main phases. The first phase being the memory profiling phase. Basically, the attacker is running on the machine, and for that, the victim doesn't have to be running. We generate a map of the memory space to identify the flippable locations in the memory. And in the online phase, the victim runs the signing operation, for example, of an ECDSA scheme, and the attacker collects the faulty signatures. And finally, in the post-processing phase, the attacker recovers the key bits using the faulty signatures. And next, we will focus on how they do that. So Rowhammer just allows you to inject faults, but we are trying to get the key bits out of this. So here we have a simple toy example to understand. Basically, we have a secret value D, and the attacker doesn't know the original data here. But we assume that the attacker can flip one of the bits in a random unknown location, and they can somehow get the error pattern delta D. And if they can get the error pattern, which is here D prime minus D16, from that, they can actually deduce what the original bit value was. So when you arithmetically obtain this error, if it is positive, it means that the bit value went from 0 to 1. And the magnitude of delta D will tell you the location of the bit. So if the error was negative, on the other hand, it means that bit value went from 1 to 0. So we use this method as a probe on the secret value, and we inject faults, and we recover the secret bit by bit. And specifically in ECDSA, we are targeting the private key D, and it's a randomly selected 256-bit integer value, and it's used in the step shown highlighted here in signature generation. So D bar is the faulty key, and S bar is the faulty half signature, and the error propagates through S bar. And in the signature verification, U1 bar is and U2 bar are faulty, so the R bar will not be equal to the original R, so the verification will fail. And note that the signature verification is a publicly available primitive, and the parameters given in green color, they are known to the attacker. So this whole thing can be computed by the attacker as well. And if we substitute U1 bar and Q in the final equation, we can show that the original R is equal to R bar plus delta D times U2 bar times P. And note that here, everything except the error pattern delta D is either public, or it can be computed by the attacker using the public signature verification primitive. So to find the delta D, we can just check all possible single bit error patterns, And since the size of the D is 256 bit, including both positive and negative values, in a maximum 512 trials, we can get the correct value of delta D. And we show that a slight variation of this attack also works for DSA, RSA, and even for EDDSA. And it also works when the fault is injected to the nonce instead of the secret key. So to inject faults to victim memory, we use Rowhammer, and for that, you need adjacent rows in the DRAM. And for that, you need to bypass virtual to physical and physical to DRAM address translations. And once you find these adjacent rows, you can profile memory for vulnerable rows. And after that, the attacker can release the vulnerable rows. And using some memory massaging techniques, the victim can be forced to the vulnerable rows, and the attacker can flip bits in the victim pages. So we implemented this attack on OpenSSL ECDSA implementation in a DDR3 setup. And in less than 2 hours, we were able to collect 515 faulty signatures. And about 92% of the time, we observed single-bit faults. 8% was double-bit flips, and less than 1% was triple-bit flips. And we didn't observe any more than 3-bit flips. And even if there are more than 1-bit flip in the private key, you can still recover them. You just have to try more combinations for delta D. And after some time, the recovered bit locations and the flip bits are starting overlapping, so you get fewer and fewer unique bits on the private key. Which means that using only Rowhammer in a limited time, you can only recover the private key partially. So how do you recover the remaining key bits? So depending on the partial leakage, there are different optimal strategies. If you are targeting the nonce, you can use either FFT-based approaches or lattice-based approach. But using only single-bit faults, which are the most common case, you would have to collect up to 2 to the 45 faulty signatures, which take a lot of time. And for a reasonable number of signatures, you need to inject multiple bit flips. But the thing is, they have to be adjacent to each other. And with Rowhammer, this is extremely rare. And if your fault injection target is the secret key, there was no known algorithm that could efficiently recover the rest of the key. Because again, the bit flips are scattered instead of being adjacent. And if the number of unknown bits is more than 50, it takes a significant time to exhaust all of them. So in this work, we solved this open problem by modifying baby step giant step algorithm, so it operates on binary representations instead of integers. I'll not explain the details, but you can find them on the paper. And with this algorithm, we were able to recover the rest of the bits with less than 1,000 faulty signatures. We also analyzed other crypto libraries. We manually reviewed the low-level signature primitives to check if there's any countermeasures against faulty signatures. And we saw that in only FIPS version of OpenSSL, they had a signature check after signing. And in Microsoft SimCrypt, they could only detect the first faulty signature. Then in a client-server setup, we injected faults into the server side and tried to collect the faulty signatures from the client side. And we observed that in all TLS implementations, the faulty signatures were actually transmitted to the client side, which enables our attack. And the Microsoft SimCrypt didn't have a TLS implementation, so it was not applicable to them. And we also disclosed our findings with the library authors, and WolfSSL, LibreSSL, and Amazon acknowledged the issue, and they worked with us for a patch. OpenSSL also acknowledged the issue, but they stated that Rowhammer and, in general, fault injection is not in their threat model. To mitigate Jolt attack, one obvious direction is to mitigate Rowhammer. And you can use, for that, you can use increasing the DRAM refresh rate, ECC memory, or TRR. But with their current state, they are either not very effective or they come with very high overhead. And against the signature correction part, you can use verify after signing, redundant signing, or masking sensitive values. And the libraries that released the patch, they implemented verify after sign to prevent the transfer of faulty signatures to the attacker. In conclusion, we proposed a novel attack called Jolt that targets signature schemes. And using signature correction and modified baby step, giant step algorithm, we were able to fully recover an ECDSA key with less than 1,000 faulty signatures. And we also analyzed several TLS implementations and observed most of them are vulnerable. And some of them still remain vulnerable if fault injection is possible in your scenario. And this highlights the fact that you need to select the underlying implementation carefully depending on the security needs of your specific application. Thank you very much for your listening.
Any questions? Okay, I have one. You mentioned that you need to do a bit-by-bit search on the key. Yeah. Do you need the private key to move locations in the memory in order to induce different bit flips masks, or can you do it in the same location?
So in the same location, the neighbors can induce only specific locations. So, and every time you run the session, it will go to a different location in the memory. So naturally, it's moving. So I mean.
Okay. So you need to do this memory massaging every time between different signatures?
Yes, yes, for every session.
Okay, thank you.
They are independent from each other.
Okay. And how much time does it take to do an overall attack with the memory massage and everything?
So we measured the online time, and it was less than 2 hours.
Any more questions? Okay, so let's thank our speaker again.